Okay, before we start looking at any actual graphs, I want to just look at the HK form. Okay, this is the basic form of any function put in HK form, which is in a lot of cases known as vertex form. So this part tells us what the function is. Okay, and that means it tells us what type of graph that we're dealing with, whether it's quadratic, exponential, any kind of graph. This is the part that tells us which graph it is, because this piece is going to be where it tells us we have either x squared, or it's linear because it's to the first power, okay, or maybe there's a radical, so it's a radical graph. Okay, so that's the part that identifies the function. Okay, well then we have our a value. Our a value is our vertical stretch. Okay, remember, it's the thing that multiplies all the y values. So if this a was a 3, then all the y values get stretched 3 times as tall. Either 3 times as tall up or 3 times as tall down, depending on where they are. But we multiply all the y values by whatever a is. So that also means if a is a fraction, like 1/2, then all the y values will be half as tall. Okay, so this value either stretches or compresses the function. Then we have our h. H is our horizontal shift. Okay, it tells you how far the graph is moved from side to side. Now remember, in the formula, this is a minus h, okay, meaning that a positive h moves it to the right. So if it says minus 5, it moves to the right 5. If it says plus 5, it moves to the left 5. And then we also have our k value. The k value works much the same way that h value does, except for it shifts vertically. Okay, so we have our horizontal shift and our vertical shift. Okay, but whereas this one works backwards, a minus 5 moves to the right 5 and plus 5 moves to the left 5, this one moves the way you would think. So if it had a plus 5, it would move everything up 5. If it had a minus 5, it would move everything down 5. Now the short of why the h works backwards is because it's happening to the x before it goes into the function. Therefore, it kind of works in reverse, whereas the k happens to the x value after the function has been applied to it. So that's why this one does what it seems like it should do, and the h actually kind of does the opposite of what it seems like it should do. Alright, so we're going to start with the linear graph. And we're going to put this in HK form, which for a linear graph is known as point slope form. And go ahead and pause it and see if you can graph this function. Alright, so I see my h here. It says plus 1, so I'm going to move left 1. And my k says minus 3, so I'm going to move down 3. So I'm going to go from the origin. I'm going to go left 1 and down 3. And then I see my slope is 2/3, or my a value is 2/3. Okay, it means everything is 2/3 as tall. Well, normally this graph would go up 1 over 1, wouldn't it? Normally it would go up 3 over 3. So normally this point would be right here. If a was 1, it would just go up 3 and over 3. Okay, but this point has to be 2/3 as tall. So I don't need that point there. I need it here, which is 2/3 as tall as it would have been. It would have been three units taller, so now it's only 2. And there's my function. Now notice, yes, this is still slope. It went up 2 and over 3, just like if you'd have said rise over run. But I just want to point out that it still works the same as all the other a values, making it 2/3 as tall as it should have been. Look, right here, it would have been over 1 up 1. Instead, it's over 1 and up 2/3. Okay, because this a value just multiplies all the y values, making it taller or shorter. All right, now we're going to look at an absolute value graph. Okay, if you graph the parent function for y equals the absolute value of x, you should be able to apply the a, h, and k to that graph to get this function. So I've got a -1, so that tells me I'm going to be moving right 1, and a +2, which tells me I'm going up 2. So right 1, up 2. So from the origin, because that's where it normally would be, because the square root of 0 is 0, that's why the origin would be on this parent function, I need to go right 1 and up 2. Okay, so there's my new point, my vertex. Now, the parent function would just have me going over 1 and up 1, over 1 and up 1. So I would have these 2 points here. Would also have me going over 2 and up 2, over 3 and up 3. Okay, because it's just a straight line this way and a straight line this way, like a V. Okay, except I have an a value of 2, which tells me that this function has to be twice as tall as the parent function. Okay, so these points have to move up. Instead of up 1, it has to be up 2. The other point also has to move up to where instead of over 1 up 1 and over 1 up 1, we have over 1 up 2. Over 1 up 2. And there's our function. Now we have the step function. I know you guys remember the step function from earlier this year. Except for it shifts around just like any other graph. So see if you can go ahead and graph this one. Alright, so this one just has an h value plus 3, which tells me I need to go to the left 3. Well, normally it starts at 0, and it has my little stair steps, right, because you already graphed it. Okay, so I need to move it to the left 3. So I just moved it over 1, 2, 3. There we go. Now this graph normally goes over 1 and connects, but is an open point because as soon as it gets to this point, it jumps up 1 and then continues. Okay, this is what a step function looks like, and don't forget it goes in the other direction too. Okay, this is called a step function. This is actually a greatest integer function, okay, because that's what these symbols mean, greatest integer. So if you have 2.2, well, the greatest integer is 2. If you have 2.8, the greatest integer is still 2. Okay, which is why this is a flat line until it gets to the next integer. Then it jumps up to the next integer. Okay, so and then it stays at that value until it gets to the next integer and it jumps. Okay, there's no way for it to ever be 1.5 because this is a greatest integer function. So every answer is going to be an integer. And that's why it looks like the stairs. Okay, but once you had the parent function, really all you had to do was shift everything to the left and you got your graph. Now we have an exponential function. Okay, so see if you can graph that, and then we'll look at it together. So in this case, notice where my h is. It's always with the x inside the function. Okay, so just because I don't have parentheses, or just because it's up here in the exponent, okay, it's always inside the function. So this minus 3 is my h, telling me that I have to shift everything to the right 3. Okay, and this minus 4 is outside the function, telling me that that's my k, so minus 4 tells me down 4. Okay, but before I'm going to do that shift this time, I'm going to go ahead and graph the parent function. Okay, because this is a base 2 exponential graph. Okay, which if you remember, gives me 3 points. If x is 0, 2 to the 0 is 1, 2 to the 1 is 2, and 2 to the negative 1 is 1/2. That gives me these 3 points. Okay, if it was just y equals 2 to the x power. So now I can shift those. I need to shift them right 3 and down 4. So when I move them right 3 and down 4, here they are down here. Okay, but there was one more piece of this graph. It also had an asymptote, remember? Okay, so the asymptote is on the x-axis for the parent function, because this graph is going to come down and get horizontal and never touch the x-axis. Because there's no exponent of 2 that would equal 0. Okay, well I need to move that asymptote as well. So it moved to the right 3 and down 4. Although I can't really tell that it moved to the right 3 because it's a horizontal line. So really it just went down 4. And then here's my graph. Okay, so this is the exponential function. This is 2 to the x, except for it's moved to the right 3 and down 4. Alright, now we better be good at this one. We spent enough time on it. This one's a quadratic. Okay, so go ahead and see if you can graph this quadratic equation or function. Alright, so I see that I have a plus 1, which tells me it needs to shift left 1. I have a plus 3, which tells me up 3. Okay, here's my h because it's inside the function. Here's my k because it's outside the function. So I'm going to shift left 1 and up 3 to get my vertex. There we go. Okay, now normally this graph, a parabola, would go over 1, up 1, over 1, up 1. Because 1 squared is 1 and negative 1 squared is 1. So normally I would have these 2 points here coming after the vertex. But this a value is negative, which means instead of going up the 1, I have to go down the 1. So these points have to flip to the other side of the vertex. And because it is 1/2, they also have to be half as tall. So this point, instead of being up 1, has to be down 1/2. And this point too, instead of up 1, has to be down 1/2. So I'm going to go ahead and move those. And then I'm going to go ahead and add one more point. You can see how I get there. Over 2 would normally be 2 up 4. Okay, except for when I go over 2, I have to go negative 1/2 as much. So instead of up 4, I go down 2. So that's how I got these other 2 points. Okay, so there's 5 points on this quadratic graph on this parabola. And there's the graph. So now we're going to look at a radical graph. Okay. So we should be able to graph this, and then we'll look at it together. All right, we have a plus 3 in our H position, so that tells me left 3. And then in the K spot, I have a minus 2, which tells me down 2. Okay, I know that because this is a radical function, that it's one of those kind of half parabolas on its side. Okay, so the vertex, so to speak, starts at the origin, so it needs to go left 3 and down 2. So I just moved left 3, down 2. Okay, and then since it's a radical function, I move over 1 and up 1 because the square root of 1 is 1. Then I move from the vertex again over 4 and up 2 because the square root of 4 is 2. And there's my graph. Notice I didn't have to stretch this one, make it taller, flip it over, make it shorter, anything like that, because my A value is 1. So everything's just multiplied by 1, which doesn't change anything. Now, the ones we just finished, rational functions. Should be fresh on our minds. We should be able to do this pretty good. Alright, so we have inside the function with the x a minus 2. So that tells me that I'm going to have to shift this to the right 2. And then outside the function, I have a plus 3, which tells me I have to shift this function up 3. So the first thing I'm going to do is shift my vertical asymptote to the right 2. Because in the parent function, as you have graphed, the vertical asymptote is on the y-axis at x equals 0. So when I shift it to the right 2, it is at x equals 2, which should make sense because our excluded value would be x equals 2, or x cannot equal 2, more specifically, because that would make this undefined, which is why there's an asymptote, a vertical asymptote, at x equals 2. Then I have the horizontal asymptote. Normally, it's on the x-axis, except for it's moved up 3 this time. So here's my horizontal. So now I have my kind of new pseudo origin here, and this is where I'm going to graph the rest of the graph from. I need to find numbers that multiply to get 8, because that's my numerator. Okay. Honestly, this is my A value as well, so I could just start with the parent function and multiply everything, make everything 8 times as tall. It would still work. Okay, but the easier method here is just to find the things that multiply to get 8. Okay. So the easiest two to use are 4 times 2 and 2 times 4. So I came over from my new origin, went over 2 and up 4, and from the new origin over 4 and up 2. These 2 points are on my graph. Then I also have negative 2 times negative 4, because that equals 8, and negative 4 times negative 2. So that gives me my 2 points on the other side. And I already know from the parent function that this is going to kind of swoop this way, going from one asymptote to the other, and this one's going to kind of swoop this way, going from one asymptote to the other. So I've got my graph. Now, one thing that I could also check too is, especially since one of the points I have is on the y-axis, I could check that y-intercept. So if I plug in a 0 for x, I get negative 2. So 8 over negative 2 is negative 4. Negative 4 plus 3 is negative 1. And the point that I plotted does have the y-intercept at negative 1. Okay, so that's just kind of an extra little check that I was able to do just because it crossed the y-axis in a nice spot. And that's the graph of this rational function. Now, this one's kind of a new one. Okay, this one is a cubic function. Okay, we have y equals x minus 4 cubed. Okay, well, you've already graphed the parent function, so we know what that looks like. Then all we have to do is apply the HK form to it. Okay, and here I have a minus 4, which tells me everything's moved to the right 4. So all I have to do is take that parent function, move everything to the right 4. Well, the parent function goes through the origin, because 0 cubed is 0. And it also goes over 1 and up 1 because 1 cubed is 1, and it goes left 1 down 1 because negative 1 cubed is negative 1. Okay, it also goes right 2 and up 8 because 2 cubed is 8 and negative 2 cubed is negative 8. So it has a little swirl like this. Up on the right, down on the left. That's what you should have got when you graphed your parent function. When I shift everything to the right, this is my vertex. 1, 2, 3, 4 places over. And then I still go to the right 1 and up 1, and to the left 1 and down 1. Okay, except for that kind of looks like it would just be a straight line. Well, but I can see that it's not, because when I go right 2, I have to go up 8. And when I go left 2, I have to go down 8. So this is definitely not a straight line. It has to come up and curve this way and then keep going up. Okay, so this is what this graph looks like. This is a cubic function. Alright, so now we have an inequality. Okay. So if you notice, this is a linear function, but it's a linear inequality. Okay, now you may have to apply inequalities to any other function as well, but I just used a linear one so that it will be easy to graph the function, and then we can just focus on the inequality. So go ahead and see if you can graph this inequality, and then we'll look at it. Alright, so first I have the y-intercept at negative 3 because that's my b, and then the slope of 2, so up 2 over 1, up 2 over 1, there's my line. Okay, so if this was an equation, if that was an equal sign, that would be the graph I'd be done. Okay, except it's not. Okay, first of all, this cannot be equal to. Okay, if it could, there'd be the other little line under here. It'd be less than or equal to. But this cannot be equal to. What that tells me is that I have to have this line be a dotted line, because this line is not part of the solution set. Okay, this line is the boundary, but it is not included in the solutions. Okay. Then it's less than, which tells me I need to shade below this line. So if I put my finger on this line and move it straight down, that's the side I have to shade. Okay, so I'm going to shade this side, and I have the graph of this inequality. The other way to check which side you shade is you can always test the origin, because it's pretty easy to test. 0, 0, and you can see if it's true. If I plug in 0, 0, I get 0 is less than 0 minus 3. So 0 is less than negative 3. That's not true. That's why I would not have shaded on the side with the origin. I would have shaded on the other side, which would have given me the same result. Okay, but that's the graph of this inequality. And then we have piecewise. This is the fun one. Okay, this is when the function equals pieces of different functions. Okay? Now, again, just like the inequality, these do not have to be linear. They could be any other type of function that we've seen and know. Okay, I just chose to use linear ones so that the graphs themselves wouldn't mess you up. You'd be able to focus on the piecewise part of it. Okay, so go ahead and try to see if you can graph this like we did earlier this year, and then we'll look at it together. All right, the first thing I do when I'm graphing piecewise functions is to graph all the functions that are included. So first I'm going to look at the top one. I have y equals negative 3x minus 4. So that gives me a y-intercept of negative 4 and a slope of negative 3. So there's the first line. Y-intercept negative 4, slope negative 3, down 3 and right 1. Okay, and then I'm going to look at the second equation, or second piece of this function. So I have a y-intercept of negative 2 and a slope of 1/4, so up 1 over 4. Okay, so that's up 1 and over 4. Rise 1, run 4. And then I'll go the other way just so I can finish making my line. Alright, so these are the two pieces of this function. Except I don't need all of each of these pieces. The second part over here tells me which piece I use for each one. Okay, so this piece tells me that the first function, the first part, is to the left of negative 2 and include negative 2, because I use this graph when x is less than or equal to negative 2. So everything to the left of negative 2 and including negative 2 is where I count the blue line. Well, here's x is negative 2. So I'm just going to start erasing the rest of it. Okay, there we go. And I made it a solid point, a closed point, because it includes negative 2. Okay, so this is the piece of this first part of the function that I need. Okay, it says y equals negative 3x minus 4 when x is less than or equal to negative 2. That's this part. Okay, then for the other part, it says when x is greater than negative 2. Okay, so greater than negative 2 would be to the right of negative 2. And since it's not equal to, it does not include negative 2, just to the right of it. Okay, so I circled it. Here's x is negative 2. I only keep what's to the right, so I'm going to erase everything to the left. And I'm going to make sure that I have a nice open point here because it's not included at negative 2. And this is this piecewise function. It has two separate pieces because I had two separate functions as part of the piecewise function. Okay, now there's no reason that these had to be different colors. I just made them different colors so it'd be easier for you to tell which one I was talking about when. Okay, this is one graph all together, and it's a piecewise graph. Okay, that's why there's only one y equals. Okay, because this whole thing is one function, one graph. All right, I just want to point out one last time that this h is always inside the function, k is always outside the function. Can scroll through all of these. H is in the function, k is outside the function. H is inside the absolute value, k is outside the absolute value. H is inside the step function, the greatest integer function. Okay, h is inside the exponent with the x. K is outside the exponent. Okay, the plus 1, the h is inside the square, the k is outside the square. I think you get my point. The h is inside the radical, k is outside the radical. H is inside the rational, k is outside the rational. If you follow this a, h, and k method, you can use it to graph any function you need.